I know my wife came in. She said, "I think you're being mean to those students." So I said,
It's fatherly love.
I said, "I am." And
It's because she walked in, she's like, "Where's Kevin?" And we're all like, "Don't say his name."
and so I said that. She goes, "Well, you need to be nice to him." I said, "No, I don't." And she goes, "At least to the good-looking ones." So raise your hand if you feel like I should be nice to you because you're a good-looking student. All right, so we got one honest guy. Okay.
You just gotta get a list.
So wait a minute.
You got a list.
I'm always nice to Mike, though. So.
I've got a great personality.
Great personality and a face for radio. Okay, we actually have to do some work. I don't have to. I don't have a test this week, so I don't really care. All right, so now we have a lot of writing to do, I guess. So put it all. Oh, I know what I wanted to do before I moved on. Based on some conversations we had during break time, because you wouldn't leave me alone. A couple things that I want to mention now, if I don't forget. So when you are inspecting anything in aviation, and our Magneto is an excellent example of that, you are asked to inspect the coil because you can reuse the coil, and you are asked to inspect the condenser. You can reuse the condenser. But in the manual, it tells you condenser to use, and I believe it has a specific thing that says or equivalent. So you can use the specific thing or anything that works. And all they're going to ask you to do is to check primary and secondary resistance, right? So what can we use to check resistance?
An ohm meter.
That's an equivalent. What must the ohm meter do before you? What qualifications must it have before we can use it?
Turns on.
It's got to be calibrated because we're using it for return to service measurement, where we're given a specific value that we must verify it's within that value. Therefore, that machine must be calibrated by a calibration lab, not zeroed out, but calibrated. Now, on the condenser, it says to use a machine and it's got some part number, and that's period. So, can we use the Graham-Lee tester?
No.
You cannot. Now, the Graham-Lee tester, you go in the back and it has all this stuff in there, and you look up your part number for the coil, and you can look up the condenser too, and it has all this data in there. Can we use that data to return to service?
No.
Why not?
It's not specifically annotated.
It's not approved data. It's not from the manufacturer. It's not approved data. So absolutely nothing about the Graham-Lee machine or the data presented in that book can be used to return this stuff to service. Now, it's completely legal to use the Graham-Lee tester, have it calibrated, and use the two settings on there to measure the primary and secondary resistance, because it meets the equivalent, but it's got to be calibrated. But then the Graham-Lee's got all these other tests that aren't mentioned at all in the overhaul manual. Can I do those tests?
Sure, if you want.
Absolutely, because all I'm doing I'm going to approve it based upon primary, secondary resistance. Then all these other things are just secondary tests to see if I really, really want to approve it. So I can get to any one of those tests and go, no, I don't like the look of that. I'm throwing it. I'm not using it, even though it passed. But we can't do it the other way around. Do you follow that?
Yes.
Okay. And so that machine for testing condensers, it's been a while. A couple years ago, I tried to find it, and it was like $20,000 or some crazy thing. So then you just think economics and how much a condenser is, and it becomes very cheap to just throw them in the trash can and buy new ones constantly for your customers than it is to buy a $20,000 machine. So anyway, so
Charge the shit out of them.
I know.
Test it.
Yeah. Well, we can reuse your capacitor for $50 or buy you a new one for $20. What would you like? All right, operation of the whole thing. Operation. I believe this is operation of everything. Let me see. Yeah, okay, this is like 3, 4, 5 pages. I don't know. Do you want me to write all of this stuff? Because I already told you. Did you take notes? Or do you want me to write all this out?
Just the important stuff.
Huh? Just the important stuff. Okay. Let's see. As the magnet is turned, lines of flux travel through the pole shoes into the coil core. We know that, right?
Yes.
Okay. So, well, this is going to get all weird. The flux periodically reverses, but is constantly
Short, moving,
changing. The changing magnitude of the flux. Let me see. The flux. This is just basically talking about AC, right? The flux periodically reverses, but is constantly periodically reverses, but constantly changing. All right. Let's see. Oh, I see what happened here. I got like a couple of pages don't belong here. It's like I redid it, and then this one got stuck in there. Operation. 1, 2, 3, 4. What the hell? 7, 1, 2, 3. All right, this page shouldn't be here. That would make sense. I hope so. All right. Voltage induced in a coil of wires proportional to the rate of change of flux. I don't want to write all that faster. Change it. Faster the change, the more current will flow. Flux linkage can be measured more. Linkage. Let me see. It must be change flux. Yeah, this is all kind of repeating what we talked about. Operation. Let me see. Yep. I think we got all this. It just. We did. We covered this pretty well. I just didn't write all the notes about it, which would take us like forever to do that. So maybe we won't. Highlights. Let's just go over it one more time. Over here. How's that sound? And you write your notes, however you feel appropriate. Where's the picture of our magneto? Way up here. Okay. So we've got the three circuits are
Primary, secondary.
magnetic, primary, secondary. Magnetic circuit consists of rotating magnet, pole shoe extensions, and soft iron core, all of which are made out of soft iron and are
Laminated.
laminated to prevent
Eddy currents.
eddy currents. Eddy currents are
Little tornadoes.
little, that cause resistance. Well, we don't want that. The magnet has two identifiable positions, which are called
Full register and neutral.
full register and neutral. In which position do we have the maximum amount of flux traveling through the coil core?
Full register.
Full register is a full register going around through that. Now, if we take just the magnetic circuit and we rotate it, we get a sine wave. And this sine wave is referred to as the static flux curve. Okay, we have the static flux curve. That is static. Well, it's not static. It means that it's moving, but we don't have any of the other components in it. As soon as we add the other components to it, i.e. the primary, as soon as we add the primary to it, and I'm trying to think if we can make this very simple. As the rotating magnet goes around, making it very simple, as the flux grows across the primary, what happens? Induces a current, and then as if it collapses, it will also induce a current. So it will induce a current going up and induce a current going back to zero, then induce it going the other way, then this way, right? It's going to just kind of keep, and if we just ran that through, what we'd end up in the primary would be this current that would somewhat follow this, if you will, being very simplistic about it. But we're going to add components that are going to change everything. And in reality, once we add the primary coil on top of the coil core, when we induce the voltage in the primary, it offers resistance due to Lenz's law to what this flux curve looks like. Because this flux curve no longer is going to be nice and neat, because we've introduced a coil superimposed on top of it that is going to have its own magnetic properties.
So it's going to be out of phase.
Yeah, I would say be out of phase. So that's where we get the resultant flux curve, which comes out and then drops off and then picks back up. And then it's kind of hard for me to, and then falls off. So we get this flux curve out of the resultant flux curve when we put the two things together. And what we're looking for is this tension. So we have tension between here and down here. That equals tension right here, right? Because it's got a long way to fall. We have tension. Tension. And when we open the breaker points, we're going to do that at E gap. At E gap. E gap stands for, what does E gap mean? Efficiency gap. And where is E gap is defined as?
The number of degrees past neutral at the points open.
E gap is the number of degrees past neutral that
The points open.
the points open. All right, so the points open right there kills off that circuit. Let me see, do I have the, no, want that. Well, so much to talk about. There we go. They don't, there we go. Resultant flux curve down here, which is what I was trying to draw. We end up with the resultant flux curve. When the points open, it kills off and opens up the circuit in the primary, which causes the rapid collapse of the primary. So here we see the primary current building up, building up, building up. And how come it didn't kind of go down in the same way?
Because the
It's a
breaker
rapid
open,
collapse.
causing a very rapid collapse.
Breaker open. So we see breaker timing point opening before neutral, closing interval, closing at E gap. So breaker point timing. Open right here. Open. Is that what they're saying? Open here. I never paid much attention to this thing right here. It's open here, and it closed. What the hell?
It's all over the place.
It's all over the damn place. Well, it makes sense if I would pay attention and actually read it. But anyway, breaker point's open over here. I'd want it over here, not over there. So breaker point's open.
In conjunction with the capacitor, it just collapses.
Rapid collapse. That rapid collapse in the primary causes secondary, which they don't even bother to put on here, a giant spike in the secondary, and there we go. So I think that was about 8 pages. Let's see. All right, we good with that?
Yeah.
Okay. Got it. When you have your oral, you have to say it with confidence. That's what we're also trying to teach you how to do oral. Be confident in your answers. If you don't know, if you have an idea, don't say it. Like, what is the where are the points open? E gap. Don't do that, right? It's E gap, right? If you don't know, capacitor. No, but half the time I'll start saying the next question. I'll go, wait a minute, what did you say? It's like it was with confidence, and I'm like, yeah. You say it with enough confidence, half the time I'll just like, I don't know, maybe I'm wrong now. This guy sounds like he knows more than I do. I better let that one slide. So say it with confidence, right? That's because when you go to the mechanic examiner, remember, I was one. When somebody's confident in themselves and their answers without being cocky, that's a whole nother thing, then you have some sort of trust. Like, okay, they believe in themselves, and it works out much better. So, all right, so we have that. See, I have some things about E gap I wanted to talk about. So. All right, operation, what about E gap? Let me see, the position of the points opening is known as E gap, efficiency gap. E gap is defined as number of degrees past neutral at which the points open. Who defines E gap?
Manufacturer.
Very good. All right, doesn't sound like I need to write that. So it's set by the manufacturer and adjusted by the mechanic. So E gap is defined by manufacturer set by a mechanic. Well, what if you bought a brand new overhauled mag, and Magneto comes in the box, you open it up, who sets the E-gap?
You do it.
Nope, it was already set. Don't mess with it.
All right. Fine, man.
Right? Don't mess with it.
I don't know. I figured you would want to double check it or something, don't you think? What if the dude?
You start voiding warranty.
Oh, yeah.
You can't double check everything.
Yeah.
Really, I opened my cell phone up every time I buy one.
So wait, the warranty gets voided when you overhaul Magneto?
hmm I wouldn't warranty it.
Now, after it's been opened already?
Yeah, they'd be like, the carbon brush is broke. Like, we'll send the whole thing in. Well, you opened it up. I'm not giving you a new car. You broke it. All right. Let's see. E-gap is different. Well, we're kind of talking about E-gap. There we go. Is different for each model. Don't assume that it's 10 degrees. You have to check it in the book. Let's see, when the breaker points open, the primary coil was holding the original field in the coil core while the magnet has already started trying to produce a flux in the opposite direction. Remember, that's the flux curve, and it's already starting to go, it's already past neutral, it's going the other direction. The action, let me see. Actions of these two together create a very rapid collapse of the primary, which induces a voltage in the secondary. Secondary has 100 times the windings. About how many turns?
Thousands.
1,000. About a total of 10,000.
That's a lot of turns.
So secondary winding has about 10,000 turns.
So that means the primary's only got a few volts even running through it at most. Correct?
No, it's about 100, I think.
Okay.
That's not too many.
Can we check it? Can you just check it with like?
We should.
Peely?
Yeah, let's do it.
Touch it.
Put it on an AC. It's AC. What kind of electricity are we producing here?
AC.
DC or AC?
AC.
AC. Got the sine wave. It's AC. So if you think about it, or don't, like this particular lead right here, where it's coming out, it may always fire positive, from positive to negative. And the very next one then has to fire from negative to positive. And that is true. So it rotates.
Huh. That's weird.
Let's see. How much voltage do we get?
12 to 40,000 volts.
Right, the amount of secondary voltage is dependent on the spark gap. So typical spark plug gap is about 0.018. 0.018. 0.018. There we go, 0.018. But air is an insulator. The more air molecules in the gap, the wider the gap will be, electrically speaking. So electrically speaking, the electricity does not see a 0.018 gap like it would out here in the regular atmosphere, because it takes a lot less voltage to jump these spark plugs right here, right now. That's why it's not a big deal. I mean, they're just kind of, I don't have to turn it very fast. You can hear them snapping away because the gaps are reasonably close. So, and the air is standard atmospheric pressure, 14.7 psi. But put this in a cylinder and boost it to a couple hundred psi, you're packing the air molecules in there, and electrically speaking, it's going to seem like that gap is about that big to electricity, right? 5-7 millimeters. That's why when we test magnetos on the test stand, we test them at a large gap, about 5 millimeters, 5 or 7, depending on the magneto. So electrically speaking, that's what that is. And I know I mentioned this before. So how much voltage we build up is all you need to do to build up to jump the gap. Once it jumps the gap, now it had a path around to ground and it completed the circuit and then it dissipates out. So see, is typical spark.
So when you talk about like weak spark, you know, your points are wearing out or something like that, or condenser's bad.
Yeah.
You get a weak spark. You're saying that, but that could be less voltage going through the secondary or the initial leads, and then it still jumps across the gap.
Okay, so if I wanted to check, I wouldn't do this on an airplane per se. Yeah, I guess I would, if I wanted to. I want to check, you have a weak spark or a strong spark. What I won't do is pull a spark plug, hook my lead to it, set the spark plug down, and rotate the engine over and watch that spark plug. Because it's just a tiny little gap. It's gonna jump it. Now, I have done it where you look at it, kind of judge by the color. If it's blue, it's a little stronger. If it's orange, it's a little weaker. But the way to do it is gap it out. Take the plug off, and like, depending on what kind you're working on, like motorcycles, we put a screwdriver inside of the ignition lead, and then hold the insulated handle and hold the screwdriver about that far away from the engine block, and let it jump a big old gap. And if it could jump that gap, then fine. If you had to hold it so the gap was only that big, well, you had a weak spark and it wasn't firing in the cylinder once you had compression on it. Follow?
What I mean is they talk about a weaker.
Yeah, it's weak.
A bad I know that, but but you're saying that it would take 20,000 for the sake of it.
Okay.
20,000 volts in order to create a spark in the engine.
Okay.
And you're saying it's going to jump when it gets to that point, right? Is that
Yeah,
what you're saying?
yeah.
So then, what if you have less voltage being applied? Now it's all.
Oh, it won't go anywhere.
It won't go anywhere. So a weak spark. It's impossible then to have a weak spark.
No.
You just have no spark.
If it's weak enough, you'll have none. So you see what he's saying? What he's saying is we have determined that the gap that it has to jump requires 20,000 volts. We're just saying that. Got it?
Yeah.
Well, what happens if the magneto can only produce 10,000 volts? You're going to give me seizures with that over there. I don't know what you're doing, but
Sorry.
yeah, it's like flashing on the whole corner. So it's very distracting. I don't like.
It's all.
Okay, just playing with this phone. So if it takes 20,000 to jump this gap and the magneto only produce 10, you won't get a spark. You'll get nothing. It builds up in the secondary and doesn't go anywhere.
Saying like what causes a weak spark though? Like when you have a weak spark.
Oh,
what-
everything. Points get burned, pitted. Well, you guys did this. It was one of your questions. E-gap starts getting off. Capacitor goes out. The coil fails.
Right. So that's what I'm wondering is like, okay, so if that all causes a weak spark, if there's a threshold to when the spark won't even jump. We're saying that if it gets weak enough, it won't start, but you can actually have a weak spark in the engine.
Not in the engine. No, you won't.
Weak spark,
What-
it just means that it's just not strong enough to do it. So it won't.
Then it would theoretically wouldn't spark at all in the engine.
Wouldn't spark in the engine. So you pull out the spark plug.
And now
You
it
lay the
sparks.
spark plug on the engine. Go, well, now it sparks. What the heck?
Oh, so there's no problem with having like less of a spark in the engine. It's all or nothing. Is what you're saying.
Yeah,
Okay.
I know, but
I didn't know that. I thought that.
well, if you have to think about what the spark plug's job is, it's to light off the fuel. And best of my knowledge, a spark is a spark.
Right.
It doesn't say, well, I don't know, you work on cars, it wasn't that was only a 20,000 volt spark, so I didn't get as much power as this guy's got a $25,000, volt jump, it's a little bluer than that guy. So once the fuel is lit off, it's burning. Yeah.
Can you have a 20,000 volt and still have a weak spark?
It either
other
s-
factors-
Okay, so to me, now we're getting outside of our books, it either sparks in the engine when it's running or it doesn't. So a weak spark, we would say stuff like that. To me, a weak spark would be something like, it sparks just fine in the engine during idle. But as you apply power, you start losing the spark. And the engine starts running bad. So you back it off, and now it idles fine. Add throttle, and it runs like crap. What's happening?
Pressure.
Pressure. When it was at idle, the throttle plate was closed, and you have low manifold pressure, which means low pressures in the cylinder. When you add throttle, the throttle plate opens up, the pressures in the cylinder increase dramatically, and the spark no longer has the ability to do its job.
And that's because there's the air is being pushed closer together, and it's having more. It's not able to jump as easily.
Now, we talked about that when you were on your phone.
So an idle, it's like closer to you doing it outside the engine with against it.
The idle is closer to outside the engine.
So the plugs are gapped in for the maximum potential pressure that's going to be on that plug then. Because if you
I suppose so, yeah.
because anything when it gets less pressure, then it's easy.
Yeah, it's just easy. So, and that is common. That is a common problem with spark engines, combustion engines, that, yeah, when things start, the coil starts wearing out, which is really on modern cars, all you have is a coil pack. When it goes out, that spark plug will fire at idle, and then it doesn't want to at higher wire open throttles.
Especially on boosted engines. As soon as
Oh, yeah,
it's
especially on boosted engines, because you're really pumping it up on there. All right, so typical amount of signal will depend on the spark plug gap. I don't know. I just threw that in there. Let's see. Well, hopefully you wrote some notes in there. 0.018 typical spark plug gap's not really relevant to what we're talking about, but I just threw it out there. All right,
What measurement is that in?
inches, feet.
Well, you
It's
were
a lot of
talking
voltage.
about like 5 millimeter gap on the Tesla stand, so.
Yeah, so that's inside the
Back
engine.
and forth.
Let's see. I've got some stuff about construction of the Magneto, which I don't know. I'm not asking you to design one, but I don't know if it's relevant. The construction of the case is let me see, 9. Construction, yeah, designed to control magnetic forces. I'll write some stuff. Let me see. Construction. I don't want to be lazy about it, but I also kind of feel like sometimes I throw out way too much information. It's like you start to lose what's important.
Do we need it?
Huh?
Do we need it?
Is it on the test?
You can just tell us if it's
Yeah.
not absolutely necessary on the test.
Yeah, it's designed to control magnetic forces. Why do we want to control magnetic forces?
'Cause that's the whole point of Magneto.
It's a big magnet and a magneto.
Yeah, what's about yay far away from it in the airplane?
Your radio system.
All the radio systems.
Magnetic compass. So you want to keep the magnetic leakage to a minimum because you got a compass sitting. Well, that's about that far in my airplane.
North
So-
is here. No, it's there. No, it's
Yeah.
here.
Yeah.
Don't doesn't the prop or the prop DI system also cause issues with the compass sometimes?
I don't know. Go back to your phone.
Google it while you're over there.
Let's see, where's that? Control magnetic forces, withstand heat, strength, and durability. Duh. Proper insulation to withstand electrical forces. Some magnetos, I don't have it in my notes, but some magnetos are pressurized.
That's part of the felt
What?
thing. That like part of the on the distributor block when they're talking about inspecting it.
Well, what you do is there's a little vent plug right there. They're just vent plugs. And you take out the vent plugs and you put in one over here that's just got a little tiny orifice in it, one over here that connects to a line that goes to what's called upper deck pressure, which is turbo outlet, and use turbo air to pressurize the magneto. Why would I want to put turbo pressure inside my magneto?
Because the plane at high altitude's got a turbo. You need turbo.
Because air is an
It's pressurized. It's not a vacuum.
insulator, and we need more
Insulation.
insulation, because if we don't have insulation, we start to get what's called flashover. These little towers are kind of close together, and we have a finger pointing at one, but if there's no insulation, it might just decide to go to the one over there. And once that happens, we start to get detonation and all kinds of really bad things happening with the aircraft. And
New engines.
yeah, and like I said, I mentioned, I had one pilot in the class who was flying Bonanza over the Arctic Ocean on his way over from Europe, and that happened to him. Non-pressurized magnetos. It was a non-turbocharged airplane, and he was high enough that it started flashing over all over the place, and he said that it did not catch and start running correctly until he was really close to the water. So it really scared them. So, but yeah, so high altitude engines that are turbocharged. If you have a turbocharged engine, a lot of times you also have a pressurized cabin. Not always, but put all those together and you got to turbocharge your mags. So I don't know. There you go. You got turbocharged mags. How about that? We don't really say that. We call them pressurized. Case is made out of, well, aluminum.
They
Talked
used
about
to be
that.
made out of magnesium, right?
Yes, the D2000s were. That didn't work out well. Let's see.
They shrunk.
All right. This is for Evan. You.
Yeah, why don't we?
Magneto speed. Just when I think nobody's going to care about this, along comes Evan. All
no,
right.
yeah, this is cool.
All right. So how fast does the magneto spin?
Half the crank.
Half the speed of the engine.
No, that's determined by a formula. The distributor spins at half the speed of the crank.
All right. So how fast it spins is actually quite complicated. And to be honest, you don't need to know this to be the best magneto mechanic ever. I built lots of engines and overhauled mags and never really cared what the ratio was. It's like, because this goes on this engine with these gears, that's the way it is. Well, how fast does that tourniquet? I don't care. It doesn't matter.
Case settled.
So, but there are some things that you might want to care about, especially if you're working on magnetos, because this is getting you in a little bit of trouble. All right, so magneto speed. I'll just follow my notes. The number of cam lobes, that's the breaker cam, right? The one that's right here on the magneto, not the camshaft, because we're not talking about engines, but this right here, that's the cam. No, by the way, I don't know, I'm feeling awfully generous today, so I'm going to let you in on a little piece of information that will ruin a lot of my fun, but we'll save you some frustration, and I don't have to worry about it because only some of you are going to hear me anyway. Printed on the camshaft in a very, very small font. If we were to take a camshaft and we were to look at it, it's got a little hole in the middle. Perfect hole. Believe it or not, there's a little arrow on there. A little arrow.
Under the washer.
Under the washer. You cannot see it. It's not a concentric cam, it's eccentric. It has a rotation. And guess what's printed on the opposite side of this cam?
Another arrow.
Another arrow pointing in the opposite direction. Which is to say, if I wanted to change this right-hand mag into a left-hand mag, what do I need to do?
Flip it around.
Flip it around.
Two things.
You need
Only have to do two things.
Remove the cam, flip the cam.
Flip it around.
I
and
have
your
to
timing button's your battery.
retime the distributor gear by about a tooth and take the cam and flip it over and put it back down. So flip over the cam, internal timing by a tooth.
So that's
They're
your
pretty
SSL
maybe
into
different
SSR
impulse.
in?
So a lot of you will put the mag on the bench and it won't run. And you will, I don't know what to do. I've taken it apart and put it back together. I've reset the time. I've spent the last 4 days resetting eGap. And by the way, you know, they say, I don't know if this is true, but people, you know, say, what's the definition of insanity?
Doing the same
Doing
thing
the
over and
same
over
thing
again and
over and
expecting
over
a different
and
result.
expecting a different result.
I got a lot of insane people in my classes, especially when it comes to measuring things.
What about the other way?
I know.
It'll change eventually.
A third time. That didn't work.
Why does this no longer
I
work?
should do it one more time.
It's like opening the fridge and expecting new food to be there.
It's
It's
exactly
worse.
like
So you set eGap and your magneto doesn't work. So what's the best thing to do?
Check your.
Reset eGap.
Yeah.
Now, if that doesn't work, the best thing to do is to
Reset
Reset
eGap.
eGap.
reset eGap. I don't know. You know, maybe third time's a charm. So I will get people do that 3, 4, 5 times. Okay, stop. Don't do the same thing over and over again. If you do that out in your job, you'll probably get fired. So yeah, don't do that. A lot of times it's just, you know, the cam's upside down. Look for something. You know, it's okay. Ask for help. My mag doesn't run. these are the things I have checked. 1, I verified that points are opening at E-gap. 2, I verified the points. Look at my work. I checked the condenser work. That's the other thing. Well, it's the capacitor. Did it test good? Yeah, but that's not the point. Can I have a new capacitor? No, you can't have a new capacitor. What's wrong with yours? Test good? Yes. All right, so be logical, right? Sometimes it's things that you haven't thought of or didn't know, like, oh, the cam goes this way because you didn't see the little printing. What's the other thing? It's the cam upside down. Oh, yeah, people take them apart all the time. Well, it must be internal timing. Well, why didn't you do it right the first time? So, anyway, there you go. Cam goes both ways. Number of cam lobes. There was a point to all this. Number of cam lobes. Change things. Number of cam lobes is equal to the number of poles of the magnet. All right, cam lobes. That's every time it's out of round. So the little drawing I did here, so expertly out of round. How many lobes do we have?
2.
2 lobes. 1 spot here and 1 there. And this right here this is the low part. And this is the low part. So 1 and 2. Therefore, this magnet had how many? 2 lobes. Okay, and 2 poles. So a 2-pole magnet has?
2 lobes.
So the formula is
1 to 1.
1, yeah, 1 to 1. There's no formula. The number of, dang it, I did it. Don't tell me now. Changed it the last time. I remember that. The number of high voltage, the number of high voltage impulses per full revolution of the magnet is equal to the number of poles.
So 1 to 1 to 1.
In other words, you have a 2-pole magnet. If it goes around 1 time, you had how many pulses?
1.
Number of high voltage impulses per full revolution magnet equal to the number of poles.
I think you'd have 2.
So you have a 2-pole magnet. Start here. So this would be full register,
Neutral. Oh.
neutral, full register, neutral, back to full register. So that was 2. Okay. So 2-pole magnet will produce how many sparks?
2.
2 for every
1 rotation.
1 rotation.
So 3 rotations if it's a 6.
Oops. All right, so I could write that. 2-pole magnet. Will produce 2 spark. I have evolutions. Sparks would have been just a much nicer word. 2 evolutions per 360 degrees. The number of cylinders that fire per revolution of a crankshaft. I don't want to make this more confusing than because it's not confusing at all.
I'm confused.
Yeah, okay. Let me see. All cylinders will fire in 720 degrees. 2 revolutions. So if I have a 1-cylinder engine, a little Briggs & Stratton on my lawnmower, if you still have a gas lawnmower, I do because I don't like the environment. How many times does the crankshaft go around to fire the cylinder? All the cylinders. Twice. What if I have Harley Davidson V-twin? Crankshaft goes around how many times to fire both cylinders? Twice. I have a 9-cylinder row radial engine. How many times does the crankshaft go around to fire all the cylinders? Twice. My engine was 6 cylinders. How many times does the prop go around before it fires all the cylinders? Twice. Okay, so I fire all cylinders at 720 degrees. So the number of cylinders that fire per revolution, one time around, would be half. Okay, that's, yeah. I think it's better to say it that way. So to determine magneto rotor speed, it is, I'll put it over here. It is number of cylinders and I didn't even want that. I want this. Number of cylinders. That was too far off.
You gotta try harder than that.
I was using the mouse.
It thinks you were making a wave.
Number of cylinders divided by 2 times number of poles. And that will equal magneto shaft speed over engine crank speed or engine RPM. All right, so if I want to know, I've got this right here. It's a 6-cylinder magneto. It has 2 poles. So 6-cylinder magneto, 2 poles. And so how many cylinders is it going to go on? How many cylinders is the engine? 6. All right, so I have 6-cylinder.
4 poles.
And 2 times the number of poles, that's 2 times 2, which is 4, equals the magneto shaft speed over engine RPM. Well, I want to know how fast this would be going on my aircraft if I was at red line, which is 2400. Therefore, how fast would this go? Well, that's X,
600?
right? So 6 times 2400 equals
14,400.
4x. So multiply that out. What do we get?
3,600.
30. No, let's finish it off here in case anybody's trying to figure out. Because if I jump ahead, somebody goes, where'd you get that number? 6 times 2, 400 equals 14,400 equals 4x divided both sides by 4. Divided by 4, 3,600, 3,600. Or, so that's how fast the magneto. Or I can do 6 divided by 4 is,
1.5.
this is right here. 6 divided by 4 is what?
1.5.
1.5. So it's 1.5 to 1. So the magneto is spinning. This is the mag.
Faster.
This is the engine. So the magneto is spinning 1.5 times faster than the engine.
You were right. Everything really is a ratio.
Yeah. Let's see. What if it's a 4-cylinder? The same thing with a 4-cylinder. So I have a 4-cylinder. Number of cylinders, 4. And we have 2 times the number of poles. So we'd have 4. So 4 to 5 is 1, so the ratio is 1 to 1. What if it's 9-cylinder
You got 9 poles on your
with a 4-pole?
4 pole.
So 9 divided by 4 is what? Oops. 9 divided by, 4-cylinder, 4-pole, so it's 2 times 4. 1.125, 1.125 to 1. This is the crank. See, it's not hard. Just a little formula. All right, see, note. Engine fires 4.5 times per revolution. Magnetic force. I figured it all out why it does that. All right. Guess we're done, huh?